Thank you for coming, everyone. No one's said it yet. I think everyone in this room already knows it, but the important thing to note about storm surges is that it's the effect of the weather on the sea surface, and as far as the hydrodynamicist is concerned, it's exactly the same physics, whether we're talking about extratropical depressions like this one here that caused major European flooding in 1953, or hurricanes here stacking up in the Atlantic in the 2008 hurricane season. How do I advance it? Just grabbing the Mac keyboard here. There we go. And of course, storm surges are devastating. We know this. We all know of examples, and thank you, Thomas, for introducing some recent examples of flooding around the world where catastrophic damage is caused. This is a diagram that's used by the World Meteorological Organization, which very sadly shows the amount of lives that have been lost globally through storm surges. And this graph shows the storm surges in Bangladesh in particular account for many hundreds of thousands of casualties. So they are still events that we need to treat very seriously and try and always increase our understanding. And just when we... Hang on a second. Right. I'm going to specifically focus on the interaction between the storm surge and the tide. And this is something we've been studying for a long time. I mean, people in Britain, in the Proudman Oceanographic Laboratory, have been studying this for the last 50-odd years. Around Europe is a highly tidal environment, and of course there's obvious interactions between the forcing terms in storm surges, where sea level is raised by gradients in atmospheric pressure. Sea level is also raised by wind stress, and that wind stress is inversely proportional to the depth, and of course the tide affects the depth. So you might expect that storm surges are affected by the tide. But of course the tide themselves, if you take some sort of very simple mathematical Kelvin wave for a tidal wave, then you would expect these additional terms of forcing on the right-hand side to affect the tide itself. And it's this mutual interaction, which has long been recognized, is the subject of this talk. And I think it's still not entirely understood, which is why I'm stood here today giving this presentation. And just when we think we're beginning to understand those factors that give rise to extremes, every year there seems to be some example, and this is just to add to Thomas's list, every year there is an event somewhere in the globe that reminds us that we need to better understand the extreme sea level in order to provide some predictability, in order to provide some protection. So there's the results of Typhoon Haiyan or Yolanda in Tacloban last year. This is a picture of the New Jersey shoreline following Hurricane Sandy in 2012. And these were the events in the UK in the year 2013, about a year ago today, where we had a North Sea storm surge that in most places was bigger than the 1953 storm surge that motivated much of this early work. The size of that particular event was of the order 2 meters, and I should just point out to those who are not familiar, tropical cyclones can give storm surges of the order 6, 7, or 8 meters. We seldom have tide gauge records in situ that properly resolve the true size of it. But the important thing, of course, is it's the summation of the tide and the storm surge and the waves and the wave overtopping that gives rise to the hazards. So understanding how all of these things vary, appreciating that mean sea level is rising, of course, is going to increase the extremes, even if nothing else does. But the interactions of these different components of extreme sea level are vitally important, and that's what we need to understand. So I just want to start first of all with the effect of the weather system on the tide itself. And back in 2007, Chris Wilson and I published a paper which showed mathematically, but quite simply, that most of the phase shift effects, where tidal high waters are adjusted, are the main effect of the weather on the tide. Now this gives rise to a residual pattern, and if you use this phenomenon, the non-tidal residual, as your key variable in analysing storm surge statistics, then it will be misleading. And this is something, Stefan, that I think we could talk about over a cup of coffee, because it's easy to show, and this is a simple cartoon almost that you could show a room of students, that if you were to advance a tidal curve without increasing its amplitude, so here for argument's sake, the solid line are observations. The dotted line is the tide that was predicted, the tide that's in your tide table. There's clearly no storm surge there. There's no change to the amplitude at high water. There's no change to the amplitude at low, to the actual height at low water. But nevertheless, the phase shift alone gives rise to residual. And in that paper, we show that the size of that residual actually scales for small angles with the phase shift itself. So the effect of the weather is to alter the phase of the tide, and that's its main effect. That's one half, if you like, of tide-surge interaction. These kind of graphs, and I'd be interested to know if these are the same sorts of histograms that we were seeing for New York Harbour earlier, simply reflect how the weather changes the tidal dynamics. So they don't actually relate to storm surge. It's simply how tides have been changed by those dynamic terms in the equations, the horizontal pressure gradients and the additional stresses. And if you try and capture the complexity of these empirical observations, and they vary from one place to another, it forces you into choosing some complex but very empirical, very spatially varying, and possibly therefore dubious statistical models that relate the size of the residual that you might encounter with the tide that it falls on and the timing. Whereas a far better measure, and this is something that certainly the Dutch have used for many years, and in the UK and I think in other parts of Europe now, we prefer to use the main measure of storm surge as the skew surge. The skew surge is a tidally cycle average measure of the difference between the height that's observed and the height that was predicted. So it's an integral measure. It reflects the amount of surge generated over a tidal cycle. It's time independent in that it doesn't vary. You only get one of these per tidal cycle, so statistically you reduce perhaps the number of measures that you have, the number of data points, but the power of that integrated measure is so much better that we now take that to be the best measure of genuine storm surge. That is the effect that the weather has actually had on the observed sea level. And so we've begun as part of a WMO project. I'm also head of an IOC expert team on extreme tides and coastal flooding to develop a global climatology of skew surges. We've begun this with the UK tide gauge network. We're very lucky around the UK. We have, and in fact many other European nations as well, have a large number of high-quality tide gauges. So we also have very high tidal ranges. It's a strongly tidal regime. This is from a port called Avonmouth, which enjoys the third highest tide in the world, after only two other locations in the Bay of Fundy. And we're starting to build up climatologies now of skew surge as the preferred metric. And I should just deviate a little to ask why no one's done this before. Why is it so hard to get a global climatology of storm surge when global climatologies of waves have been available for quite a long time? If you go to the internet, there are various sites where you can find global properties of waves. This is a climatology of significant wave height that comes from voluntary observing ships, so these are observed parameters. And if you go to this particular Global Atlas website, for every month of the year, you can find climatology of a number of key wave variables. So why is it so difficult to do that for storm surges? Because obviously globally we'd like to know what these climatologies are. And here are some of the reasons. There's no voluntary observing ships for storm surges. By their very nature, they're coastal phenomena. In the open ocean, there's no constraining coastline, so the effects of wind stress are simply to cause a surface current. Many wave climatologies come from satellite measurements, and of course, satellite measurements of individual episodic events are not sufficiently accurate that we can build up a reliable database. And of course, there's no systematic approach to getting storm surge out of tide gauge records. There are ad hoc ways of separating the tropical and the extratropical. And as yet, we don't have a single global numerical model that we can use for long runs, long hindcasts of storm surges. Most of the well-validated operational models that we use for storm surge forecasting are local. So what did we find? So here's some results again from this, this tide gauge at Avonmouth with a very high tidal range, nearly 15 metres. We find that the skew surge on the y-axis is statistically independent of the tide on which it falls. So the tidal predictions here, just to take a simple example, so here's a fairly large skew surge that occurred on a large tide, but here's a larger one that occurred on a much smaller tide. So we find that there's this independence. That's true as well. Even if you go beyond the top percentile, we still find that there's independence even in the extreme. So no matter what tail assumptions you make, we still return to this independence. Here's another one, again from the same western part of the UK. The tidal range here is 10 metres. So again, for a large tidal range, we're seeing independence. And we find this all around the UK. We've also looked at some Dutch data. I'd very much like to look at some US data. I was saying earlier that there's no consistent approach to the way that we isolate these records. Well, I suspect that many of the people in this room here, if we sat down together and came to an agreement today, we could agree upon a consistent approach. But certainly around the 42 gauges that we've analysed, the correlation is virtually zero. And so this independence of skew surge from the tide on which it falls massively simplifies the creation of joint probability. So if your approach to extreme sea levels is to take joint probabilities where you convolve the distribution of the tide, which is deterministic, with your best fit, be it GPD or GEV, of the skew surge, then you can convolve any skew surge with any tide. It might have a very low probability, but there is no reason at all why the highest storm surge should not fall on the highest tide. And this is slightly counterintuitive because one of the static terms that gives rise to storm surges in the first place is the wind stress, and the wind stress can be parameterized like this with the drag coefficient and the square of a wind speed, and then a depth term, which of course would vary in a region with a 15-meter tidal range, that would vary by a great deal. So why in fact does not the tide seem to modulate the skew surge that's generated? And here's a very simple plot. This again just assumes this static assumption where you take the stress term in a vertically averaged equation of motion and you equate that to the sea level gradient. You can do more complex analyses and you can actually take the real terms from a numerical model, which of course is not static. So as an assumption here, I've used a wind speed of 15 meters per second and squared it. I've assumed a depth of 30 meters, which is typical of a large area over which a storm surge might get generated in shallow water, a typical drag coefficient as used in a numerical model, and then plotted that over the course of a tidal cycle. There's 12.42 hours here, it's a semi-diurnal tide. Although there is nonlinearity, because this bottom term here is 30 plus the tidal variability. The blue line shows a neap tide, the red line shows a spring tide. So there is some nonlinearity which is evident, but when you average it over the tidal cycle, or indeed take its integral, then it's insignificantly different from just assuming that there's a constant depth in the first place. And so because this is a tidal cycle, it's consistent with the timescale over which a surge is generated, and that might explain why then the nonlinearity in depth does not modulate the surge generation. Just to let you know, we're placing all of these analyses on a repository on the NOC website. And it sort of leads us to understand that if you want to then truly understand what it is that makes one storm surge vary from the next, it's the details of the weather system. There are some complex tools that allow you to analyze how veering of the wind speed, small changes in the weather systems affect an individual event. This is a result from an adjoint model that we published earlier last year. And it shows that, in fact, there are concentric ripples of sensitivity to where the sea level, in this case, is most sensitive to any error in the weather model. So you can use adjoint functions to construct, if you like, a worst-case weather system for any particular location. So to conclude then, we need to understand how storm surges interact with other factors, particularly tides, if we're going to help engineers derive their extreme sea levels. We acknowledge that mean sea level rise alone is going to increase the occurrence of extremes. The effect of the surge on the tide then is to alter the timing of the of the tide itself, and that's the effect of the weather on the tide. But from decades of data, we find that tides don't modulate surge generation, so we conclude that surge magnitude is going to be determined by the variability in the weather, which is large. This means that any skew surge can occur on any tide, and we're now trying to extend this work to see whether it's true of tropical cyclones as well, and I'd welcome the opportunity to work with anyone here to do that. So thank you very much.